So I'm a PhD student, Alessandra Dolmeta, PhD student from Politecnico di Torino in Italy. This work has been conducted actually not only at Politecnico, but also at CA in Grenoble during an internship I had last year at the second year of my PhD. And I'm grateful for being here today to present in this technical session TYRCA, that is, as the acronym say, a RISC-V tightly coupled accelerator for code-based cryptography. So this talk will focus on how we can effectively integrate post-quantum cryptography into RISC-V system with a concrete case of study that is HQC, that is one of the last candidates of the NIST competition. We will see all the detail through the presentation. So there is the outline of my talk of today. So I will start with a short introduction to post-quantum cryptography and the standardization process I was mentioning before. Then I will move to some background in order to describe HQC, which is the algorithm at the center of this work. And after that, I will discuss the different integration methodologies that exist in order to integrate an accelerator in RISC-V and explain what the Xilinx is, which is the main character of this work, and it plays a crucial role in our approach of integration. And then finally, we can come up with the hardware design and implementation details of TYRCA, followed by performer result, final discussion, and after that, I will be glad to answer any of your questions. If you have some doubts during the presentation, you can write in the chat, and then we will discuss, if possible, at the end. So let's talk about post-quantum cryptography and what it is. I cannot really ask you to raise your hand if you ever heard about quantum computers, because actually I can see the chat, but I imagine that all of you at least have heard about it. And as many of you can know, quantum computer pose a fundamental threat to today's crypto system, because algorithms like RSA or ACC, so elliptic curve cryptography, which are the backbone of secure communication of nowadays system, would be actually broken by sufficiently powerful quantum computer through Shor algorithm. This is not an actual reality right now, but it could be possible in the next year. And to better understand why post-quantum cryptography come in play and the difference between post-quantum cryptography and quantum cryptography, let me walk you through this table showing the slide. So what we have is that post-quantum cryptography, differently from the cryptographic system that are used nowadays, are problems that are designed to be resistant both to classical and quantum computer, while quantum cryptography instead utilize more complex principles like superposition or entanglement. So they are, let's say, a step above with respect to post-quantum cryptography. And the security of post-quantum cryptography is generally, as I said before, based both for classical and quantum computer, while quantum cryptography is thought to be secure against the quantum eavesdropping. But the key point of the difference between these two kinds of approach is in terms of implementation, which is also the point of this presentation, actually, because PQC is much more practical. What we have is that PQC runs on today's infrastructure, with software update, of course, ad hoc hardware, which it's better in order to run this kind of algorithm, but it's different from quantum cryptography because quantum cryptography, on the other hand, needs highly specialized hardware, such as photon sources or optical fiber. We will not go into that direction in this presentation, but this was just to show you how PQC, at least for now, is considered the preferred migration path for securing communication, and also the only one possible, actually, because we have not still so commonly used quantum computers around. So the point now is that who is in charge of deciding which algorithms are secure and which are not in this standardization process. And that responsibility falls to the National Institute of Standards and Technology, that is the NIST, label NIST. And this is a US federal agency that develops, in general, technologies, metrics, and standards to promote innovation and ensure security across industries in different fields, actually. But in the field of cryptography, NIST play a central role in defining this standard and how they should be adopted. In particular, from 2016, NIST has been running an open competition-like process that is used to evaluate candidate post-quantum algorithm. And over the year, we saw submission from different cryptographic family, which range from lattice-based, code-based, multivariate, hash-based, and isogenous. And in particular, in 2023, so we are talking about 2 years ago actually, they released the first standard, which are the ones shown in the yellow block. And we are talking about 4 Federal Information Processing Standard, which were Crystal Kyber, Crystal Dilithium, Sphinx Plus, and Falcon. But the process has not stopped there, because we need additional algorithm, and especially in terms of KEM, which are key encapsulation mechanism, we have only Crystal Kyber, and this is a lattice-based algorithm. So this process is going on in order to select one algorithm that is coming from the code-based family. We will see later what code-based mean. And so this process continued to evolve. In 2024, there was the 5th NIST PQC standardization conference, and they selected 4 different round finalists, all belonging to the code-based categories, which were BIKE, Classic MacLIS, AQC, and Cyc. That is the one below the X, because actually Cyc has been broken, so it has been excluded from the competition. And exactly this year, in March, AQC has been actually selected for standardization. And this makes AQC a very relevant and timely target for hardware accelerator. This is why it has been selected as the target of this work. This standardization process, however, is not going on only from the mathematical point of view, of course. We have basically 3 different layers. Of course, mathematics is one of the most important, because we have to analyze the security foundation of the different algorithm, and providing the strength, the hardness of this algorithm against a possible quantum attack. The second aspect is usually software, of course, because again, we need efficient implementation, optimized encoding, compiler support, and everything is needed in order to run this algorithm. But these 2 layers, of course, are not enough, because as I said before, this kind of algorithm are running on today's platform. So to make post-quantum algorithm truly feasible on today's platform, hardware support is essential. And we are talking therefore about accelerator, custom instruction, FPGA or async implementation, because without dedicated hardware, many of this scheme, the one I mentioned before in the NIST competition, would remain too slow or too energy hungry to be adopted in practice, because the key point of their hardness is, of course, that they are more complex from the computational and the mathematical point of view. So my research actually lies in this 3rd layer. So we are talking about the hardware perspective, where the goal is to make PQC not only secure, but also fast and energy efficient on constrained device. And this is exactly where RISC-V makes the difference. Because thanks to its open and modular design, RISC-V allows us to experiment with custom instruction set extension, specialized accelerator, coprocessor, and everything without the barriers of proprietary ecosystem. For PQC, moreover, the flexibility is a fundamental part, because we have seen that the selection of this algorithm is continually evolving, and we need architecture that can evolve with the algorithm themselves. So RISC-V gives us the freedom, and it is the reason why so much cutting-edge work in this field are actually using RISC-V as their ecosystem. So now, since we have outlined, let's say, the motivation and the challenges of this field, we can now look at the background of the algorithm. I will ask for mercy for every mathematician that could possibly attend this speech, because I'm not a mathematician. As Rafael said, I'm an electronic engineer, so I will try to explain you a little bit the base of the maths that is behind the code-based cryptography and AQC, but I will say I'm not an expert. But let's see where code-based cryptography is born. So the origin of this approach go back to the studying of error-correcting code, which were designed to ensure a reliable communication over a noisy channel. And the idea in this case is really simple. What we have is that a sender is trying to transmit a message. It encodes it into a longer sequence that is the one defined as a code word. And if some bit flip due to noise in the channel, so due to the noise that is present in the communication channel between the sender and the receiver can still reconstruct the original message by running a decoding algorithm. As I said before, we will not delve into the mathematical details, but these are the main concepts that should be known. So the mathematical backbone of code-based cryptography is, of course, the definition of linear code, that is the C here represented in the slide. And the linear code can be defined in two different ways. So we can have a generator matrix that is G and tells us how to build the code word itself. Or we can have another definition that is using the parity check matrix, which let us detect a correct possible error. So seeing if it's a valid code word or not. Indeed, starting from the parity check matrix, so the H matrix, what we have is that given any received vector R, the product between the transpose of R and the parity check matrix give us the syndrome. This is another concept that allows us to understand the syndrome decoding problem, because the syndrome provides a compact description of the error pattern, and it is the central part of the coding algorithm, which are the base of code-based cryptography. And so recovering the error vector given a syndrome, so given an S vector, it is the one known as syndrome decoding problem. And in the general case, this problem is considered computationally very hard. And that, therefore, is effectively this hardness that is what made code-based cryptography eligible for as a candidate for post-quantum cryptography selection. Historically, the most famous code-based algorithms are the ones shown in the picture. So the first one was Mekeli's crypto system, actually, from 1978. So we are talking about tens of years ago. And it was based on GOBA code. It has resisted cryptanalysis for over 4 decades through the cost of a very large public keys. And that's why different other algorithms were introduced in the game. In particular, a researcher turned out with a new series of code, which are the quasi-cyclic code, that allows a much more compact representation. And this led to the different algorithms RISC-V there, and that was mentioned in the NIST standardization process of the introductory part, like BIKE, LedaCrypt, Mekeli's, of course, Cyc, and HQC. Many of them has been discarded because they were not considered secure anymore. They were broken by some mathematician. But in general, you can see that there are many options, and that this made code-based cryptography a very mature and well-studied field, because it offers strong time-tested security, and with the use of this kind of structured code, it becomes really practical for real-world deployment. So we need to consider the trade-off between compactness, efficiency, and also conservative security margin. And that's effectively for this series of reasons that HQC has won the competition this year, and it has been selected to be standardized. So HQC stands for anti-cycle. So we are talking about this quasi-cyclic structure code I was mentioning before, and it is based on the hardness of the syndrome decoding problem. It combines 2 different linear code with a specific error distribution, and it offers 3 different levels of security, which are HQC 128, HQC 129, and HQC 256. It consists, like any other CAM, so any other key encapsulation mechanism, of 3 different main operators, which are the first phase, that is the key generation, in which public key and private key are generated, the encapsulation phase, in which the secret key is encapsulated using the public key, and then the decapsulation phase, in which the secret key is decapsulated using the secret key generated previously. So, of course, all these mathematical details are important. I am trying to give you a little overview, but what we are interested more is the hardware point of view of HQC. And so for us, what really matters are the bottleneck of this algorithm, where we are trying to run it on a given platform. So in practice, this means that we are interested in the profiling of HQC. So we are looking at the latency, the number of clock cycles that take each function when running each function on an FPGA or a SoC. And we need to identify which part dominates the overall execution time. So depending on this analysis, we are able to decide which function need to be accelerated and what instead can remain in software. And considering this perspective, we started our analysis by profiling the lowest level of security of HQC on a 32-bit SoC. We use official software implementation, the latest one, or at least it was the latest one, because actually they released a new version like 1 month ago. And what we can see from the table is that polynomial multiplication is by far the dominant cost in all the algorithm. And this is mainly due to a shift in the multiplication strategy, because we have that early code-based scheme we're using a sparse to dense multiplication. But for security reason, HQC had to move to a dense to dense approach. To be concrete, this means that every coefficient of one polynomial in the multiplication must be multiplied with every coefficient of the other. And the result, of course, is then accumulated and reduced by a polynomial. But the point is that this quadratic complexity, of course, increases the amount of time that is spent in the multiplication. In fact, as you can see, in both key generation, encapsulation, and decapsulation, this takes the highest amount of clock cycle with respect to the overall function. Other two bottlenecks are catch-up, that even if it's contributing minimally to the overall runtime, it is used across a different function, and it is a function that is operated on a state that is 1,600 bit, and that's the main reason why it is so heavy when run on system on chip that are on 32 or 64 bit. And the third element we have considered is Reed-Solomon code that are used during encoding and decoding that present a notable bottleneck. We will see later which part of this decoding is actually accelerated, because we have not considering the whole function. So now that we should have a little bit understand what HQC is, we can see the different integration methodologies that RISC-V offer. Because the question now is how we actually accelerate the block I have just shown you. So which is the best method we can use in order to address this bottleneck? So roughly speaking, there are three different possibilities in order to integrate an accelerator into a RISC-V environment, which are a loosely coupled approach, a tightly coupled approach, or a coprocessor. So starting with the first, a loosely coupled accelerator is like an external device. So it is connected through a RISC-V system, generally using a bus like XC or AHB. And it usually can run in parallel with the CPU because it is like an external device, and may also exploit, for example, the DMA, so a direct memory access device, to talk directly with the memory. The drawback is that the overhead of moving data back and forth through memory is quite important when considering applications like post-quantum cryptography, where there are many data that need to be exchanged each time for each function. But it has the pros of not requiring any HISA extension, because it is usually called through a controller or a driver that is implemented in software. Then we have the tightly coupled accelerator approach. In this case, tightly coupled accelerator, on the other hand, are usually integrated very close to the core. So they can access to the register file directly, and they must work in synchronization with the CPU. So they cannot work in parallel because they're basically part of the core. The drawback here is that they require modification of the pipeline, so of the decoding stage, the execution stage, and of course all the connections that are between them. So it's quite more intrusive with respect to a loosely coupled approach. And also they require, of course, a new set of custom instructions in order to be called. And then there is the third approach I was mentioning, that is the coprocessor. In order to better understand what I mean when I talk about coprocessor, it's better to compare it with the tightly coupled approach. So what we have is that unlike the tightly coupled accelerator, a coprocessor is in the pipeline of the CPU, but is not actually integrated inside it. So what I mean is that instead of being inside the CPU and instead of need to modify every component of the CPU, usually the coprocessor is connected through a dedicated interface. And this means that we don't need to modify any of the internal stage of the core, which makes the solution far more portable across different RISC-V implementation, because as long as the core supports the coprocessor interface, we can plug it in different accelerator, in different cores, without redefining the entire processor. And this is why coprocessor integration is often seen as a good compromise between portability and performance. Also, when considering data, what we have is that the coprocessor can work with its own external register file, or also directly with the register file of the CPU. But this can make the design also a little bit more complex, because in the case we need to add an external register file, we can do it, and we can address it outside the core. So in short, the coprocessor gives us a clean and extensible way to integrate new functionality, but without the intrusiveness of tightly coupled change. And here come the interface I was mentioning at the beginning of the presentation, that is the Xilinx interface, the Core V extension interface. This is a new interface that has been introduced and then is today handled by Open Hardware Group, and they provide the benefit of tightly coupling, so it has the direct access to the register file and of course a really low latency, but without modifying the CPU and all the internal logic, as I was mentioning. And it works thanks to a dispatcher. So this dispatcher is basically collecting all the signals that are needed from the RISC-V CPU, and pass it through this interface to the coprocessor, and then it's the coprocessor who handles everything and will perform or not the operation depending on what the CPU is asking. And this is the key point of my work, so of TYRCA. Here there is an example of the CV32E40PX, which is basically the RISC-V, the P version, to which it has been added the dispatcher, that is the small block in orange, and the Xilinx interface. And this is exactly the core that we have used during this work. So let's see quickly how this interface works. So what we have is that when the CPU encounters an instruction that the CPU don't recognize, so a new custom instruction, it tries to offload it through the issue request channel, the one in red, to the coprocessor. And this packet of signal basically contains the instruction encoding, the thread ID of the request, and a unique identifier for the instruction. Then the accelerator replies with an issue response packet that can either accept or reject the instruction. Of course, it rejects it in the case it is an illegal instruction and it is not in the set of instructions that the coprocessor can actually execute. But if it accepts it, so it means it recognizes the new instruction as a valid one, the CPU provides the operand, so RS1, RS2, and also RS3 is possible because we have 3 different source registers, directly to the register interface to the coprocessor. And then the coprocessor can finally execute the instruction, saying the core that its commit is valid. And after executing the instruction, what happens is that if the core is prepared to receive the result, so we have that both result valid and result ready are one, so are valid, the result is written back in the register file of the core at the destination register that was pressed with the instruction the clock cycle before. So this is the timeline and the handshake of how the Xilinx works. So now that we actually seen the background of HQC and how TYRCA has been constructed, so the idea of coprocessor that is tightly coupled to the core, thanks to this new interface, we can finally see the implementation details of TYRCA. So we build TYRCA on the top of the core I showed you before, so the CV32E40PX. As you can see from the picture, there is then the reference at the end of the slides, that is extended with this new interface. The entire system, it's made of course, a TYRCA accelerator, the RISC-V core, an instruction and data memory, the JTAG module for debugging, and a UART for communication. And then there is, of course, the OBI bus that is connecting everything. And it is the block that is shown on the right part of the slide. The key message, of course, is that TYRCA is integrated into the processor as it was part of the CPU, but as I said before, without intrusive change to the core architecture. TYRCA itself, so the coprocessor, is basically made by two main contributors, which are the Xilinx controller, that is the one that handles the interaction with the RISC-V core, so it takes all the signal that I described in the previous slide, and the different accelerator, which we can see are three main class of accelerator that are the R unit, the RS decoder, and catch-up unit. So the three main bottleneck that we have seen when we were doing the HQC profiling. So each accelerator is customized to execute one or more instruction, depending, of course, on the one implemented, and they are called depending on the instruction that is sent from the core side. So as you can see, the Xilinx controller basically decode the instruction and then select the accelerator that should be activated and the different multiplexer that should be used in order to propagate the result back to the core. So the most important accelerator in TYRCA is the one of the R unit, which implements the polynomial multiplication using Karatsuba. We have seen before that polynomial multiplication is the main bottleneck of the HQC, and that's why this is the most important accelerator, because the polynomial multiplication was taking more than the 95% on the overall execution. And what we have is that the reference software implementation was actually using and working with 64-bit integer. But since our version operates on 32-bit, because we have a 32-bit system on chip, what we are doing is basically breaking each of these two inputs in two chunks of 32-bit each. And we have implemented 4 different custom instructions in order to handle all the different inputs and be able to write back the result properly, because we have a result that is on 128-bit that must be split 32-bit at the times, therefore 4 custom instructions. And as you can see there, this is the 4 custom instructions that we have implemented. And we have that with the first custom instruction, we take the first 2 parts of the input and we already are ready to write back the less significant bit of the result, so the less significant 32 bits. With the second instruction, instead, we are writing back the most significant bit. And then with the third and the fourth instruction, we are writing the 64-bit that are in the middle, let's say. From an implementation perspective, so as you can see from the picture, basically, the accelerator comprises a unique carryless multiplier, along with, of course, all the necessary logic that is needed to manage the different inputs, to store the intermediate result, and combine the different parts of the result with XOR operation. So the key takeaway here is that the R unit is not just a direct translation, let's say, of Karatsuba, but is specialized for field arithmetic in order to exploit the property of carryless multiplication and to achieve, of course, a higher performance with respect to the software version. We will see later how much is actually this improvement in terms of performance. For what concerns instead the Reed-Solomon decoder part, we have identified 2 main bottlenecks that are the GF, so Galois field reduce instruction, and the carryless instruction. So starting from GF reduce, which is the one shown in the algorithm, what we have is that this is an operation that should simply reduce a polynomial modulo, a given primitive polynomial. So it should be just a reduction. But the point is that in software, this is implemented as a kind of long division. So what we have in software is that at each step, you need to extract the higher order part of the polynomial, shift it, XOR it back to cancel the term beyond the field sites, and then the remainder need scanning non-zero term. So there is another operation that is the trading zero. So many operations are involved. It's not so important which of them. But what is important is that if done in software, this kind of operation involves many conditional and intermediate results, which make it quite expensive. And to address this bottleneck, what we have introduced are 2 custom instructions, which are GF reduce 1 and 2. And basically, we have that GF reduce 1 perform the initial reduction, and it extracts the higher order bit, applying the modular correction directly, so without the need of explicit masking and shifting. And the second custom instruction updated the remainder polynomial, by incorporating the new shift distance directly, so eliminating the need to recompute shift position in software. With this extension, so the hardware essentially implement a lightweight reduction engine, so just shifter XOR, which make the critical loop that was present in software slower with a minimal hardware cost. The second part of the RS decoder instead, the second is implemented, is the GF carry-less multiplication, which is in software a multiplication that is performed between two 8-bit polynomial and produces a 16-bit result. The problem again is how it is implemented in software, because in software we have a windowed method that comprises a pre-computation of a small table of partial product. Then we have to scan the input in 2-bit chunks, and then using a constant time masking to select the right entry of this small table. And in software, this requires a lot of loop, a lot of masking, and repeated computation. Again, if this is done in hardware, we can reduce a lot the number of clock cycles needed and the number of instructions needed per step. And so what we have done in hardware is expose this selection step directly with 4 custom instructions. So each extraction basically corresponds to one of the 2-bit windows I was mentioned before, and it immediately returns the correct partial product from the lookup table. Then the different 4 results that are obtained are of course combined still in software, but we reduce a lot the number of instructions that are needed in the inner loop. And the last block is Keccak. Keccak accelerator is a little bit different with respect to the other. So if you remember well, we were talking before about one possibility of using a coprocessor with a custom interface, that is the possibility of having a dedicated register file. In the case, the instruction we want to perform is more complex than the common RISC-V instruction. And this is exactly the case of Keccak. Because Keccak is an hash function that operates on a state that is 1600 bit and requires 24 rounds of permutation. So the main challenge in this case is that 1600 bit cannot fit in the register file of the CPU. And to solve this problem, what we are doing is basically loading the entire state of Keccak in a dedicated register file that is present in TYRCA. And therefore, in this case, we introduce simply 3 custom instructions. One that is used in order to load the state. So basically, we are loading 64-bit of the Keccak state per instruction until we have completely filled the register file of TYRCA. Then we have a start instruction that triggers the 24-round permutation, and we have 1 permutation per clock cycle. So we have that the Keccak accelerator is taking 25 clock cycles in order to terminate its permutation. And then we have a store instruction that writes the result back to the CPU 32 bits at a time. From the implemented point of view, Keccak is made of a state register, this dedicated register file that is connected to the state, and then the Keccak core that is implementing the 5 transformation step of a round of permutation that is then repeated 24 times. So now we are finally coming up with the conclusion of our approach, and we also try to compare it with other solution that was present in the state of art at the time. So first of all, how these accelerators are actually called. So we have a recap of the different custom instructions that I have described you in the previous section. And what TYRCA is doing is exposing the different accelerator to inline assembly. That is a way to call the different accelerator inside the C code. So we are using a directive that is the instruction directive that can call R type or R4 type of RISC-V instruction, and specifying in the opcode the function field, we are invoking the proper accelerator in the code when it is needed. This keeps software integration simple and transparent without requiring compiler modification, so without the difficulties that we usually encounter with tightly coupled accelerator. Here is an example. So this was Karatsuba optimization. So we have the C function of Karatsuba that was making the base mul multiplication, so the Karatsuba multiplication between the 2 inputs A and B. And what we do is substituting this common instruction with our custom. And you can see on the right part of the slide the 4 Karatsuba instruction I have described before. So we have, of course, a pre-processing step because we need to split the 2 64-bit input in 4 32-bit inputs. We pass it through the coprocessor, through the instruction directives, and then we combine back the 4 32-bit part of the result in the final result that we had before. The first analysis we have done, so if the first set of results that we have collected are comparing the original software function against the accelerated one. So we have the 4 class of instruction described that are Karatsuba, GF carry less, GF reduce, and Keccak. And as you can see from the table, we have speed ups that range from the 1% to the 99%. So Karatsuba, that was the main bottleneck of HQC, is actually the one that is optimized the most, because we have that in software, it required more than 6,000 clock cycles to be executed. We are talking about clock cycle, while when accelerated with the 4 custom instruction, it takes only 52 clock cycle. Of course, all the code was compiled with the same level of optimization and run on the same FPGA with the same environmental condition. Overall, if we consider instead the overall execution of HQC, so the 3 different levels of security and the 3 different steps that we have for key generation, encapsulation, and decapsulation, we have a speed up that range between the 17 times and 21 times with respect to the original code. So we have the software clock cycle on the top of the table and the clock cycle achieved with the different accelerator integrated. Everything has been run on a Xilinx Kintex-7 FPGA, using specifically the Diligent Genesis 2 board, and everything from synthesis to place and route has been done using Vivado. Here we reported some error result in order to see how much TYRCA occupies in terms of loot and register with respect to the overall system. And as you can see, the main contributor actually of this area is Keccak because of its huge state. But if we not consider that, actually we have, for example, the R unit, which is the one that is giving the highest speed up, that is occupying less than 1 kiloloot and fewer than 300 registers. So a really low area occupation with respect to the other part. When it comes to result for this acceleration, and we try to compare it with other work present in the state of art, we have to admit that a direct comparison is quite difficult. It's not straightforward because, as I mentioned before, HQC changed from round 3 submission to round 4, so last year basically, because it passed from a sparse to dense to a dense to dense multiplication. So here in the table, there are, for example, 4 work that was found in the state of the art, but they were all done before 2024. And so they were using the previous version of HQC that is completely different with respect to the one that is using Karatsuba. And TYRCA at that time was the first one that instead implemented the latest version of HQC with the dense-to-dense multiplication approach. We still try to make a small comparison by considering slices, for example, with their work. So we're considering, since we were implementing the design of different FPGA, slices, which are unit that can be considered quite common also between different families of FPGA. And we introduce a new figure of merit that is considering not the overall clock cycle, because as I told before, it is quite difficult to compare them if we consider 2 different version of HQC, but we consider speed up over slices. And as you can see from the table, TYRCA was showing quite impressive result, in particular quite similar if we consider the entire accelerator, so considering Keccak, RS decoder, and the Karatsuba multiplier, that is the second row of the table. But if instead we remove Keccak, that is the one who is contributing the most to the overall area, we have actually that the speed up of slices is almost double with respect to the other case, because the improvement in terms of performance are still quite high, but the area is almost halved. So we are finally coming to conclusion. AQC, we have seen that is an emerging algorithm. I have just told you before that they actually released a new version last month, so it's continually evolving. We are not arrived still a complete standard, but it has been selected to be standardized. So it is good to work on it. And TYRCA was one of the first tightly coupled acceleration solution for RISC-V architecture that was accelerating the AQC, exploiting this new interface of the Xilinx. And we also achieved a relevant speed up that was between the 17 and the 21 times the software implementation across all the different levels of security of AQC, because the accelerator we have implemented are the same between all the different levels. And therefore, this underscore TYRCA potential in robust post-quantum cryptography, establishing this new standard that is still ongoing and underdeveloped. So thanks. There is the bibliography first, so all the work that I have cited during the presentation. And now thanks everyone for your attention. Here there is the QR code. If you're interested in some more detail on the work, you can find it already online.
Thank you very much, Alessandro, for your presentation. Thanks for all the insights and great content. So we have some questions in the chat. Let me start from the first one.
For now, interrupted the presentation. Otherwise, I will not read it.
Yeah. First one is from Kartikeya. Sorry for pronouncing the name wrongly. But how is coprocessor methodology different from loosely coupled method?
So the coprocessor methodology is directly, I don't know if during the presentation I have more or less answered to the question already, but the main difference is that loosely coupled method is connected through the core through the bus. So it's not directly connected to the core, and it can work therefore in parallel with the CPU. While the coprocessor is more similar to a tightly coupled accelerator because it's connected directly to the CPU. It cannot work in parallel with that. You need to work in synchronization with the core. And so let's say it's a sort of way in the middle between the two approaches. I don't know if I answered to the question.
So, yeah, maybe Kartikeya, so if you need any follow-up on the question, please let us know. And then there's a CJ Kieran, another question, main drawbacks of coprocessor methodology.
So the main drawbacks are, of course, related to the interface itself, because it's less easier with respect to a loosely coupled approach to actually integrate the coprocessor in other core. If the core supported the interface uses, it's really simple. But if the core is not supporting it, it means that you have, in the case, for example, of the Xilinx, integrating the dispatcher inside the new core. So it becomes quite complex as the tightly coupled approach. But if the core you are using has already the dispatcher and has already the Xilinx integrated, the Xilinx or another interface independently of on which one you are using, it becomes really easier. It depends on the core and on the environment you're actually using.
Moving on, we have one more question. Let me get it here from Dr. Nasser. What is the difference between the tightly coupled processor and custom instruction?
I don't think that there is actually a difference, or at least we have that tightly coupled processor must be used with custom instructions. So let's say that the custom instruction are the way with which we are able to call and address to a tightly coupled processor. Otherwise, we will not be able to use it basically.
Another question we have here is from AJ, is how your work fits into VLSI.
I don't know if I actually get the question. If you can be a little bit more specific.
AJ, can you elaborate more on your question, please? So if you want to speak, I can let you just raise your hand and I can let you ask you verbally. So while we're waiting for AJ, so from Vivav, what is the effect of quantization on acceleration of cryptography algorithms? What is the effect of quantization on acceleration of cryptography algorithms?
It's not actually a problem for this kind of post-quantum cryptographic algorithm because they all works with integers and basically handle polynomial, matrix, vector of polynomial, and therefore we are not talking about quantization, but we are talking about the reduction. And so we have to be quite compliant with the reduction strategy that I use in software, because otherwise there will be security problems. So it's not, we cannot go so far away from the reduction methodologies that are used in software, because otherwise we will risk to reduce the security of the algorithm. So we cannot talk actually about a quantization, effect of quantization, because we need to be strictly related to what is happening from the mathematical point of view and from the software point of view, in order to not affect the security. So I see that it has added how TYRCA fits into VLSI about application. I still not getting your question. If you're talking about the different application, basically the main point, as I try to explain at the beginning of the presentation, is make this algorithm more suitable to system on chip that are used nowadays, because otherwise implementing this kind of algorithm is usually quite expensive. It takes a lot of time and especially a lot of memory. In the case of Accelerator, some of these bottlenecks, some of these computationally heavy part on hardware, we are able to make them more fitable, let's say, to the different systems that are used in these days.
We have more questions that just landed. So from Lancelot, during standardization, we will then move to the custom instructions to a standard RISC-V extension and port them to LLVM.
This is the idea. We are actually working on it, but it's still an ongoing process. We are trying to do that not only for HQC, but also for other algorithms. But we are doing it with my group of research. I think there are other groups that are doing the same. I know that there is already a group in RISC-V that is actually thinking about it. So probably there will be a standard someday. There is already one for cryptographic algorithm like AES or RSA. There is not still one for PQC, but I think the community is working on that.
Good to have more questions from Rayfan. How long have you pursued this topic? Can you share the challenge you have faced during your research?
I'm at the third year of the PhD, so now it's 4 years. I'm basically approaching to this field because I also done my master thesis on this topic. Being an electronic engineer, as I mentioned before during the presentation, I think that one of the most challenging aspects are the mathematical one, because it's quite difficult to understand the mathematical background of this kind of algorithm. And I have to admit that usually you don't understand everything of it, actually, or still I don't understand every aspect of this algorithm. But one piece at the time, you are trying to make it work. From the hardware point of view, I've been studying electronic engineer for 5 years, so it's a little bit more easier to try to find a different solution.
We have two more questions here. How does HQC is vulnerable to SCA attack?
I know it is vulnerable, and there are some aspects of HQC that are still under development for this reason, but I'm not an expert of side channel attacks, so I cannot say you precisely with what aspects are. I know that one of the greatest problems was this sparse to dense multiplication, the one I've talked during the presentation. And in fact, they have to pass through a dense to dense multiplication. This was, for example, one of the problems HQC had. But the other problems that are still remaining, I will not tell anything about it because I don't know it actually.
One more question that came from CJ Kiran. How tightly coupled integration can affect in FPGA implementation issues?
One of the main problems you can have is actually that the designer will not fit in the time constraint you have before. So you have the possibility to maybe have introduced an accelerator with a critical path that is too long, and therefore the frequency of the device can become slower. But usually, if you are putting the right register before and after the different accelerator that you are integrated, it should not be a problem. And this is the case, for example, of the Xilinx if, because you have register before executing the instruction that are taking the source register from the core, and then the registers that save the result for write it back into the core. I think this is one of the main problems you could have actually, because usually in terms of area, for example, there should not be any problem, at least of course you have not implemented a huge block. For the moment, I have no other idea actually. I think the timing could be the major issue that you can have. Yeah, I see that you are asking also for the slide. I will for sure send them to Rafael. Okay, I'm seeing the other questions. So I am a final year student working on a project relating to designing a custom RISC-V processor for battery management in electronic vehicle. I'm planning to implement it in 3 stages. Okay. Could you please suggest how I can approach this project more effectively and what improve? Okay, maybe sorry if I not pronunciated it well. Maybe you can write me an email if you want, so we can talk it maybe later, since I see that the processor you're working on is a little bit different from the PQC accelerator we were talking here. So I don't know if you have seen the email from the slide. Otherwise, it's just my name dot surname at polito.it if you want. Or also you can find me on LinkedIn.
We are approaching the end of the hour. Is there any more questions, folks, that you would like to ask?
I have to read another question. Yeah, I don't see any more question, I think.
Yeah. So if you have any more questions, say you can reach out Alessandro directly. I think she's open to answer any questions and even provide more details to that student that is looking for some feedback. So Alessandro, I'd like to thank you a lot for your presentation, a lot for your time dedicated to RISC-V and sharing this with all here. This recording will be available between today and tomorrow on our YouTube channel. And again, Alessandro, thank you very much.
Thank you, Rafael, for inviting me. It's been a pleasure.
Thank you, everyone. See you in the next technical session.
Yeah, sure. Thank you. Thank you all for attending the presentation.